Hello, I am Gabriele Russo from the University of Rome Tor Vergata, and I am presenting MEAD, Model-Based Vertical Autoscaling for Data Stream Processing, which is a joint work by myself, Valeria Cardellini and Francesco Lopresti from the University of Tor Vergata, and Giuliano Casale from the Imperial College London. Data stream processing can be regarded as the reference paradigm for real-time data analytics. Data stream processing applications ingest continuous and fast data flows, called streams, and process them with very low latency. Applications are usually defined as directed cyclic graphs, where vertices are called operators and are interconnected by data streams. Operators are processing elements, usually threads or processes, that apply some transformations or functions to the incoming stream and output a new stream as the result. By chaining and interconnecting multiple operators into a graph, applications can implement possibly complex queries on the input stream. To deal with large amounts of data, operator execution is often performed in a parallel and possibly distributed fashion to exploit the parallelism provided by computing infrastructures. Data streams are often generated by a multitude of sources and possibly upon the occurrence of real-world events that we want to analyze to extract some insights. For these reasons, it is not surprising that the data generation rate and hence the application workloads are highly variable. Therefore, it is difficult to statically provision computing resources to DSP operators without incurring the risk of resource over-provisioning or under-provisioning. Elasticity, that is the ability of dynamically scaling resources as needed, is thus regarded as a key feature for data stream processing. Elasticity so far has mainly been implemented by means of horizontal operator scaling, which consists in changing the number of parallel instances run for the operator. This enables efficient utilization of multiple cores and nodes, but often comes at the price of significant overhead, because specific protocols must be used to preserve state and stream integrity in the process. An alternative mechanism is vertical operator scaling, which consists in changing the amount of resources allocated to the existing operator instances, for example memory or CPU shares. This usually comes with negligible overhead, but provides limited scale-up capacity, as you cannot scale beyond the capacity of the machine where the operator is hosted. Elasticity in the field of data stream processing has been an active research field for more than a decade, with a variety of solutions being proposed. As mentioned, so far horizontal scaling has received most of the attention, with a few exceptions including QFling, a work close to ours being presented within CCGrid 2020. In general, in the literature, solutions differ from each other with respect to several dimensions, as for example, the reference metrics considered for scaling, the control architecture, and the methodology used to devise scaling policies. What we observed is that most of the existing policies rely on simple performance and workload models. For instance, they often rely on queuing models where Poisson arrivals are assumed, and the workload is usually characterized looking at the average arrival rate only. We are interested in investigating what happens when the input stream is bursty. Few works have considered burstiness effects on DSP autoscaling so far, and mostly looking at throughput instead of latency, which is critical for many applications. So to demonstrate the impact of burstiness, we performed some preliminary experiments in which we compare different models for response time evaluation of Flink operators. Specifically, we consider the well-known MG1Q, the GG1 using Kingsman approximation, and the MapG1Q, where we consider the Markovian arrival process, which allows us to capture non-exponential and possibly correlated arrivals. We consider two public real traces. The first one is extracted from a dataset of New York City taxi trips. The second one, indicated as Live Maps backend, instead contains requests to a remote storage system, and is from the Microsoft production server traces. Both represent relevant use cases for data stream processing, as applications can be fed either with events coming from everyday life or with system-generated data to be analyzed. We can note that the traces are quite different. They show a similar average arrival rate, but as shown in the slide, the live maps one shows significant burst, while the taxi trace has an almost constant rate. The diversity of the traces is also evident looking at the autocorrelation of the inter-arrival times they contain. We observe that arrivals in the live maps trace are autocorrelated differently from the taxi trace. So we measured the response time of a Flink operator under these two workloads and compared it to the estimated values. We can see that under the uncorrelated taxi trace, all the models match well the measured response time, both at low and high utilization. Conversely, under the live maps workload, only the map-based model is able to provide accurate estimates, with the simpler models failing to estimate the response time by more than one order of magnitude. So it is clear that under bursty workloads, if we do not account for burstiness, we may end up with very inaccurate performance predictions and so bad scaling decisions. Therefore, we aim to design a model-based autoscaling solution for DSP called MEAD. MEAD relies on vertical operator scaling, and specifically we consider a scenario where at runtime each operator can be associated with a CPU configuration among a set of M configurations. Each configuration provides a different speed up and is associated with a different cost, where the cost, for example, may be monetary in a cloud setting or just represent the impact on energy consumption. We chose to focus on vertical scaling, which hasn't been extensively explored for DSP so far for various reasons. First of all, when horizontal scaling is used, input streams are partitioned among parallel instances, potentially mitigating burstiness effects due to correlation between consecutive arrivals. Therefore, vertical scaling is the setting where accurate workload characterization is most needed. And this situation is especially relevant for applications running in resource-constrained environments like fog and edge, where acquiring additional CPU cores may be not trivial. To drive scaling, we aim to build accurate workload models online and exploit the resulting models to predict performance and make decisions. MEAD is organized according to the well-known MEAD pattern for self-adaptive systems, which revolves around four key functionalities, that is monitor, analyze, plan, and execute. So we have a workload monitor that collects information about the input data stream. Such information is analyzed by the workload analyzer, which builds workload models, and then by the performance analyzer, which makes prediction based on these models. In the planning phase, the autoscaling manager uses the available performance estimates to decide whether to scale or not. And finally, a resource manager performs vertical scaling reconfigurations. Markovian arrival processes can be regarded as extensions of continuous time Markov chains, where state transitions are either hidden or observable. So a n-state map is defined by two matrices, which specify the hidden and observable transition rates. A map can model a sequence of inter-arrival times by associating an arrival with each occurrence of an observable transition. This means that the inter-arrival times correspond to the time between two consecutive observable transitions. Hidden transitions instead only change the state of the process. An important property of maps is that they can model correlated arrivals. This is not the only kind of model able to capture such autocorrelation, but differently from models like RIMA, maps can be efficiently used within queuing models because we have tools like the matrix analytic method for their analytical resolution, so we don't need computationally expensive simulations. For online workload characterization, we would like to derive a map model given an observed sequence of inter-arrival times. where the model should match the statistical properties of the trace. This is a difficult problem because to impose the statistical properties of the map model, we have to simultaneously manipulate several nonlinear matrix equations, and we can only do it efficiently for very small models. In practice, fitting algorithms try to accurately fit only a limited set of descriptors, such as the first 2 or 3 moments of the interarrival times and a set of autocorrelation coefficients. The approach we consider in this work is based on the Kronecker product composition and is a divide and conquer approach. Instead of directly fitting a large model, we fit J maps with 2 states, for which we have closed formulas that allow us to easily impose statistical properties. Then KPC is used to compose these models into a final model with 2 power j states. This works well thanks to the properties of KPC, which allow us to easily relate the properties of the J maps to the properties of the composed model. An implementation of this method is provided by KPC Toolbox, which is an open source project. Now, these activities are usually performed offline, so the traditional problem consists in finding a model that accurately matches a large historical trace. Instead, we want to characterize the workload online. To do so, we let the workload monitor component record the interarrival times of the input stream. Clearly, this stream is unbounded, so we store the interarrival times in a fixed site buffer and use a first in, first out policy to remove all the observations from the buffer. Periodically, a snapshot of this buffer is provided to the workload analyzer that fits a map model. This is apparently easy, but involves a few additional challenges compared to offline fitting. For instance, we must keep in mind that the available fitting algorithms seek the highest possible accuracy looking at a limited set of descriptors. And since we run it online, we also look at a limited segment of the input stream. So we should avoid the risk of overfitting. In this aim, instead of returning a single fitting solution, we return a set of the best candidate solutions found. In this way, we can derive multiple predictions, and to be safe, we can make, for instance, scaling decisions based on the worst scenario. Moreover, it is not obvious how long our monitoring window should be, or in other words, how far in the past we should look to characterize the workload. Because a long trace provides more information about the process and is generally better, but the shorter the window and the faster we detect changes in the arrival process. So to avoid relying on a single static configuration, we decided to use multiple windows. Basically, we start with a base window size that equals the size of the buffer, and we additionally fit maps on shorter traces that we obtain looking at more recent subsets of the buffer. For instance, we can pick the second half of the base window. Once we have obtained some maps, we need to use them for autoscaling. We model DSP applications as open queuing networks where external arrivals are generated according to the fitted map, and operator instances correspond to single server queues. The operator service process is assumed to follow a phase type distribution, whose parameters are estimated offline. We use the matrix analytic method to solve the queuing network, and specifically we use it to evaluate either the mean end-to-end response time or its percentiles, depending on the given requirements. The autoscaling problem we aim to solve consists in minimizing a cost function, which accounts for the cost of the CPU configurations granted to each operator. As mentioned, this cost may model a monetary cost or other resource-related aspects. The cost minimization is constrained by the response time requirements specified for each path in the application graph, which usually correspond to different queries computed by the application, which may be more or less latency sensitive. We use a greedy heuristic algorithm to solve the problem. We start by selecting the cheapest configuration for each operator. Then, for each path, we first evaluate the achieved response time. If the requirement is satisfied, we are done. Otherwise, until there is some operator that can be scaled up, we scale up the operator with the largest response time and re-evaluate the achieved performance. As a final check, we revert the scale up and stop the algorithm if we detect a response time improvement smaller than a given threshold. This avoids unnecessary scaling of non-bottleneck operators in situations where we cannot meet the requirements. At the end, we return the CPU configuration to use for each operator. We implemented MEAD on top of Apache Flink, leveraging a Rabbit message queue for stream ingestion. The workload monitor exploits the fan-out exchange of RabbitMQ to set up independent message queues so that the workload monitor receives a copy of each input element of the stream and consumes it independently from the application itself, which is not impacted by such monitoring. The workload and performance analysis is performed by new components that we introduce, which are implemented using MATLAB and exploit two open source projects, KPC Toolbox and Line, which is a solver for performance and reliability modeling. These components communicate with Flink and specifically with the Job Manager component. Vertical scaling is implemented by means of Linux C groups, which allow us to dynamically provision and limit CPU shares available for operator threads. For evaluation, we consider three traces: a synthetic trace which contains 4 segments, each sampled from a different map and showing varying levels of burstiness. Then we consider a trace of network traffic captured at the Belcore labs, which is known to be a challenging trace for fitting. And finally, we again consider the live maps backend trace we used in the motivating example. As shown in the slide, the traces show different correlation levels. We consider a reference DSP application which processes system logs. We will consider a maximum response time to be guaranteed along the path, specified either in terms of mean value or 95th percentile. We first consider the synthetic trace and require the mean response time to be within 100 milliseconds. The trace starts with a Poisson arrival process, and every 10 minutes the process changes to a different map. Looking at what happens with the GG1 model, we see that it simply doesn't detect any change in the workload. On the top right, we see instead that the map-based models allows the autoscaler to detect the workload variation and scale up the CPU allocation to meet the requirement. For comparison, we also run a popular threshold-based policy which scale up or down the CPU shares based on the current utilization level and predefined thresholds. It performs better than the GG1 model as it partially reacts to workload changes, but it still fails to meet the requirements. Now we consider the live maps trace, which is much more bursty, and for this reason we set a less strict requirement of 1.5 seconds. This experiment confirms what we saw in the previous one, and it is even more evident how inaccurate simple models can be. The map-based policy is a bit too conservative in this case, but manages to keep the response time within the bound with a mean value of 0.75 seconds, differently from the alternative policies. Finally, we consider requirements in terms of 95th response time percentile. We show that results for the Belcore trace and the live maps one. Again, we see that the map-based scaling policy meets the requirements, whereas the traditional MG1 based model does not. We don't consider the threshold-based policy here as it is unaware of the different type of response time requirement. To summarize, we presented a model-based solution for vertical operator scaling that relies on online workload characterization by means of maps to estimate performance and make scaling decisions. Our solution, MEAD, has been shown to satisfy response time requirements under bursty workloads. For future work, we plan to extend MEAD to jointly control horizontal and vertical operator scaling, so to leverage multiple scaling mechanisms. And we also aim to explore more advanced models to better cope with the effects of back pressure and stream fork joints. Thanks for your attention.